The study of algebra is made up of a variety of different subtopics. Two of those topics I'll be explaining in this video are equations and inequalities. I'll explain how they are connected to each other and how they can be graphed to show the solutions for each of them. This should give you a better understanding of how equations and inequalities are built up from each other. I've also created previous videos called Basic Algebra Part 1 and Part 2 and Slope from Points and then Equations. Both of these videos can be found on youtube.com under my name, Ron Cox. I strongly recommend you watch Basic Algebra Part 1 and Part 2 before you watch this video. It will help you to better understand what I'm doing in this video. Then watch the video Slope from Points and then Equations after viewing this video. Here are several basic types of equations and inequalities a person would learn about in beginning algebra. I'll briefly describe each one of these, then I'll describe them in detail one by one later on. Let's begin by looking at the overall meaning of each of these algebra statements. An equation or an inequality consists of two distinct sides, a left side and a right side. The difference is that either the two sides are equal to each other, or one side is larger or smaller than the other side. The first one here is an equation. It states that the left side has to be exactly equal to the right side. It also happens to have a number missing on the left side. The next two are inequalities. The top one states that the left side always has to be less than the right side, and a number happens to be missing on the left side of this inequality. The one under it states that the left side has to always be greater than the right side, and as in the previous one, it also has a number missing on the left side. The next one on the bottom left states that the left side has to be equal to the right side, but here you have two missing quantities, x and y. Again, I'll explain this in detail along with the others in a minute. The two on the bottom right are inequalities. The top one stating that the left side always has to stay smaller than 12, and the one under it says that the left side always has to stay greater than or more than 12. Both of these also involve two unknown or missing quantities, or x and y values. There are several ways in which you can read or interpret equations or inequalities depending on what it is you're trying to do with them. Take a look at this basic equation. Are both sides equal to each other as this statement claims? In order to be sure, you first have to mentally add both numbers on the left side, 12 plus 3, to see if it's the same as 15, and it is 15. Now look at the second one. Is the left side really equal to the right side as the statement claims it to be? I doubt if anyone can answer that question without first simplifying the numbers on the left side, then on the right side, and comparing them together. 8 plus 2 is 10, minus 4 is 6. 1 plus 5 is also 6, so they are equal. So the statement is true. This next one is where it gets really interesting. In order to verify that the equation is equal, I first have to simplify the left side to one number and compare it to the right side. When you have a string of different arithmetic operations to perform, you have to do them in a certain order. Here I have to first do the multiplication 2 times 6 to get 12. Then I have to add 12 to 3 to get 15. So this equation is true. The left side is equal to the right side. This is what a typical two-step algebra equation would look like, only in a real problem one of the numbers would be missing or hidden from you. For example, let me cover up or hide one of these numbers so you can't see it anymore. Let me hide the 6 by covering it up with a symbol. I'll use the X symbol to cover it up. It could be any symbol, even a question mark, but since people usually use symbols like letters from the alphabet, I'll use the symbol X. Now remember, when we use alphabet symbols in math, they are not letters like you would use them in writing. They are just meaningless symbols used to cover up or hide numbers in an equation. You could use a picture of a soccer ball if you wanted to hide a number, but it would be awful hard to keep drawing a soccer ball each time you wanted to show an unknown quantity. Now let's spend a few minutes on this example to make sure you understand the different ways in which you can work with an equation. This information is important for understanding more complex equations and inequalities. In this example, I've hidden one of the numbers on the left side of the equation. This represents a typical equation to be solved. I won't explain the rules of basic equations here since I've already covered that in my video Basic Algebra Part 1 and Part 2 on YouTube. Unlike the previous version of this equation where everything was given, this one now has a missing or hidden number and I have to do some work to figure out what that number is. Using the rules or laws of equations, I'm going to take it apart. First, I have to subtract 3 from both sides of the equation to get 2x on the left side and 12 on the right side. Then I have to divide both sides by 2 to get the x alone on the left side, and the number I was looking for appears on the right side, which we already know is 6. You can see this if I uncover the number on the left side that I covered up before to see that it's 6. Now suppose I wanted to hide the 2 instead of the 6 and then solve for it. Then I place the x over the 2 to hide it and solve the equation. But first let me read what it says. It says I'm multiplying a hidden number by 6, then adding 3 to it so that it has to be the same as 15. Now that I've read it and understand what's there and what's hidden, I can now go through the steps to solve for the hidden number. Just like in the previous one, I have to get the covered number, or x, by itself on one side, and a single number on the other side by applying the rules of algebra. First, I subtract 3 from both sides to get rid of the 3. Next, I divide both sides by 6 because I have to undo the 6 that's multiplying the unknown or hidden number to get 2 on the right side. So, the hidden number is equal to 2. If I move the x symbol from the original equation, you can see that it's 2. Now suppose I wanted to hide the 3 and let someone else solve for it. First, I have to read it to see what's going on here. I'm multiplying 2 times 6, then adding a hidden or unknown number to it so that it all has to be equal to 15. So what's the hidden or missing number? Now we systematically take it apart to find the hidden number, again using the rules of algebra. I can first simplify the 2 times 6 to get 12. Next I have to subtract the 12 away from the left side to get the hidden number alone, which means I also have to subtract the 12 from the right side to keep the equation balanced. Now the hidden number is alone on the left side, and I simply look on the right side to see what the hidden number is supposed to be. I see it's 3, and if I uncover the hidden number in the original equation, it's 3. Okay, one last example. Suppose I wanted to hide the number on the right side by placing the x symbol over it. This would be an example of a basic arithmetic problem where you're given some arithmetic operations and asked to find the answer. On the left side we have 2 arithmetic operations, and on the right side is where the answer would be. I'm going to read it first, then solve it for the hidden number. When I multiply 2 times 6, then add 3 to that, what do I get? Following the rules of algebra, I have to multiply 2 times 6 first to simplify it to 12. Then add 12 plus 3 to get 15. So the answer or hidden number here is 15. The reason I took this simple equation and hid the various numbers in it was to show the fundamental nature of an equation. It's important to know this in order to move on to more involved situations when an equation has 2 or more unknown quantities in it, or when solving and interpreting inequalities. As you can see here, I systematically hid or covered up each of the numbers in this equation and then used the rules of algebra to figure out what the hidden number was. This is what algebra is used for, to find a hidden or missing number in an equation. Now let's go back to the original equation, 2x plus 3 equals 15. The solution to this equation is when x equals 6. How would you show or represent this solution on a number line? Remember, the solution to this equation is 6, and only 6. No other number will work in this equation. So how do you show 6 on a number line? This is a typical number line extending from all the positive real numbers to the right of 0 to all the negative real numbers to the left of 0. This is how you would interpret or show the solution for an equation with one missing or hidden number. It is one specific point on a number line. It will be different when you have 2 or more unknown quantities or for inequalities. Okay, that covers equations with one unknown. Now for inequalities with single variables. How do we handle a situation when 2 sides of a math relationship are not equal to each other as in these two? In the first example, it states that the left side always has to stay smaller than 15. It's not easy to tell what numbers will work for the unknown quantity. Unlike our previous problems, where one number worked, in inequalities there's an infinite number that will work. And in the bottom example, it states that the left side always has to be larger or bigger than 15. When the inequality symbol points in this direction, or to the left, it means less than, or smaller than. There's several ways to remember this, and I'll show you one of them. First of all, if I place a number on the left side of the symbol, such as 4, what am I allowed to place on the right side? Well, if the number on the left side has to always be smaller than any number on the right side, then I can place any number on the right side as long as it's bigger than 4, like 5, 6, 7, 10, and so on. If I flip the symbol over so it points in the other direction and again place the number 4 on the left, what am I allowed to place on the right side? Since now the number on the left has to always be larger than whatever is on the right, the only numbers I can place on the left have to be smaller than 4, like 3, 2, 1, minus 1, and so on. So how can you remember which side has to always be bigger and which side has to always be smaller? We can use dots to do that. What I'm about to say applies to societies that read left to right. Some societies read right to left, so it would just be the opposite for them. If you can read these two symbols by themselves, it will make it easier to interpret inequalities when solving them. I'm going to place dots on the points and ends of each of these symbols. Now, reading left to right, you encounter one dot first and two dots second. One dot is less than two dots, so this top symbol means less than or smaller than. Reading the bottom symbol left to right, you encounter two dots first, then one dot second. And two dots is more than one dot, which means that when the symbol points to the right, it means greater than or more than. So how would you draw a greater than symbol? Well, when reading left to right, you encounter more dots first. Then just connect the dots. How would you draw the less than symbol? Well, reading left to right, again, you encounter one dot first, so you draw the dots, then connect them for the symbol. Let's go back to these two inequalities. Now that you know how to read the less than and greater than sign, you should know that for the top inequality, we have the less than symbol, so that means that the left side always has to be smaller than the right side. So what numbers am I allowed to plug in for x so that when I multiply it by 2 then add 3 to it, it will always be less than 15? When you have an equation, you solve it for the missing piece and only one number will work for x, or the hidden number on the left side, which happens to be 6. But for an inequality, there's a whole bunch of numbers that will work to make the left side always smaller than 15. But it's not easy to see which numbers you can plug in for x that will always make sure that the arithmetic on the left side will always be smaller than 15. But we can solve this similar to an equation to see what numbers are allowed and what numbers are not allowed to be plugged into the left side. So let's solve the top one and see if we can figure out what it means. As I said before, you solve this inequality like you solve an equation. The object is to get the missing piece on one side and a number on the other. According to the rules of algebra, I subtract 3 from both sides first, then I divide both sides by 2 to get the x alone on the left side and the number 6 on the right side. Okay, let's read it. It says x, or the numbers I'm looking for, always have to be less than 6. Remember, I was looking for numbers that I could plug into our original inequality to make sure that 2 times that number plus 3 will always be less than 15. So as long as I pick numbers less than 6, 2x plus 3 will always be less than 15. What are some numbers that will work? 5, 4, 0, minus 5 are all less than 6. Plug one in and check it out. Let's try 4. When I plug 4 in and do the arithmetic on the left side, 2 times 4 is 8, and 8 plus 3 is 11. You can see that 11 is less than 15. So the truth of the original statement is correct for x equal to 4. The truth statement will always be maintained as long as I always choose my x values less than 6. What if I tried 7? 2 times 7 is 14, plus 3 is 17, and 17 is certainly not less than 15. So for any numbers greater than 6, the truth value of the original statement is not upheld. The statement will only remain true for x is less than 6. How would you show the solutions to this inequality on a number line? Remember our first example, which was the equation 2 times a hidden number plus 3 had to be equal to 15. For that example, only one number worked to keep the statement true. That number was 6. For our inequality, the left side always has to be less than 15. That means that any number less than 6 will keep the inequality true. Now we can't count 6 because 6 could not be less than 6. So we have to use an open circle to show that we can't include 6 as a solution. So every number to the left of 6 would make sure that the left side of the inequality would stay less than or smaller than 15. How about the other inequality? This one says that the left side always has to be greater or more than the right side. So solving this one leads to this situation. When will our choice for x be larger than 6? In order to keep the original statement true, we can only use values for x that are greater than 6, like 7 or 8 or any number higher than 6. This solution on a number line will look like this. Any number to the right of 6 would keep the original inequality true. That covers equations and inequalities that involve one unknown or a single variable inequality. What about equations with two unknowns and inequalities that have two separate unknowns in them? First, let's look at equations that involve x and y variables. You saw that equations with a single unknown have exactly 1 point for an answer, and it can be shown on a simple number line. But this equation has two unknowns in it, and how do we interpret that? First, let's try and figure out some x and y values that will keep the left side equal to 12. First, we have to make up a table of x and y values. Now I have to choose these x and y values so that they add together to equal 12. If I randomly choose x equal to 2, then what does y have to be to keep the left side equal to 12? Well, I have to figure that out. I have to now solve for y by subtracting 2 from both sides to get 10. Y has to be 10 so that 2 plus 10 is the same as 12. What if I want to make x equal to 4? What does y have to be if x is 4? Again, I have to figure out what y is by subtracting 4 from both sides to get 8. So I solve for y when x is 4 to get 8. So if I use 4 for x, y has to be 8 to make x plus y equal to 12. What if I choose 7 for x? Again, I then have to subtract 7 from both sides to figure out what y has to be. It's 5 if I make x 7. Let's find one more pair of numbers. I want to make x 9, which means I have to subtract 9 from both sides to get y equal to 3. I could have also picked the y values, then worked backwards to find the x values if I wanted to. As you can see, I could go on forever picking values for one of the unknowns, then pairing up that with the other unknown value to make sets of solutions for this equation. There's a standard way to write these pairs of x and y values for a two-variable equation. It's called ordered pairs, and it's written in parentheses where the x value is always first and the y value goes second. The reason they're called ordered pairs is because they are in a specific order with the x value first and the y value second. It will always be this way in this order. Now let me write these pairs of solutions I found in ordered pair form. The first one, 2, 10, becomes a point 2, 10. 4, 8 becomes a point 4, 8. 7, 5 becomes the ordered pair 7, 5, and 9, 3 becomes the ordered pair x 9, y 3. I found 4 of the infinite number of xy pairs that satisfy this equation. Now that I've done that, how would I graph these 4 points or show these points on a graph like I did with the previous examples we did? When you have an equation with a single unknown, you can show it or graph it as a single point on a number line like this. But when you have two unknowns and you want to graph them, you have two directions or two axes to show the x direction and the y direction together. So I have to place a vertical line here along with the horizontal x line. The vertical line is a y line or y-axis. The center point, or the point where the two lines meet or cross, is the 0 point for both lines and is designated as the point x equals 0 and y equals 0. When you move up in the direction from the center point, that's the positive y values. When you move from the center point to the right-hand direction, that's the positive x values. When you move to the left from the center point, that's the negative x values. And when you move in the downward direction from the center point, that's the negative y values. Now let me add a set of grid lines to these two axes so I can count points in any direction. Then I need to locate points 2, 10, 4, 8, 7, 5, and 9, 3 on this graph. For the first point x equal 2, y equal 10, I have to start from the center 0, 0 point and move 2 units to the positive x direction. Then I have to move up 10 units in the positive y direction from there to get to the location x equal 2, y equal 10. For the second point x4, y8, I first move 4 units from the 0, 0 point to the right on the x-axis. Then from there I move 8 units up in the y direction to get to the location x4, y8. For the next point, I move 7 units over in the positive x direction on the x-axis. Then from there I move 5 units up in the positive y direction to get to the point x7, y5. Now for the last point, I move 9 units over in the positive x direction, then 3 units up in the positive y direction from there to x9, y3. Now if I wanted to, I could have moved in the y directions first, then in the x direction second. But since the x values are always first in the points, it's probably a good idea to move in that direction first. If you notice, these points seem to be lined up in a straight line. And indeed they are on a straight line. If I connect them by drawing a line through all of the points, this line represents all of the solutions or pairs of numbers that will make the equation x plus y equal to 12 always true. So this is what the graph of all the solutions of the equation x plus y equal 12 looks like. If I pick any points from this line and plug them back into the equation, it should always keep the equation true. For example, it looks like the line goes to the point x11, y1 located here. I can check it by plugging in 11 for x in the equation and 1 for y in the equation and do the arithmetic to make sure it's equal to 12, and it is. 11 plus 1 is 12. It also looks like the line goes to the point x6, y6. I can check to see if it is on the line by plugging in those values into the equation. When x is 6 and y is 6, it does equal 12. How about the point x2, y3? That doesn't look like it's on the line. I can check it by plugging it into the equation, then doing the arithmetic to see. When x is 2 and y is 3, that adds up to 5, which is certainly not equal to 12. So the point 2, 3 is not on the line, nor is it a solution to the equation x plus y equals 12. Only the points taken from this line will keep the equation true. One more thing about lines in a plane. Lines can be thought of as one solid strip, or they can also be interpreted as a bunch of points infinitely squeezed close together to each other with no spaces in between. When working with equations, it's better to think of lines as an infinite number of points close to each other with no spaces in between. And in our example, we only found 4 of those points on the line. Remember, there's an infinite number of points on the line that we could have also found. Basically, all we wanted to do was to show or find the line that represents the equation x plus y equals 12, and this is what it looks like here. The next thing to do is to look at the inequalities that involve two unknowns. There are several steps involved in finding the x and y combinations for these two different inequalities. First, I'll read them starting with the top one. It states that I have to always make sure that when I choose an x and y value and add them together, the sum always has to be less than 12. For the bottom one, it states that the sum of x and y values I pick when added together has to always be more than 12. Okay, so how do we figure out which x's and y's to pick to make sure these statements remain true? The first step is that when you have a less than or greater than inequality, you have to first change the inequality sign to an equation and find the line of that equation by simply replacing the inequality sign to an equal sign, then graphing the line of that equation. We already know what the line of the equation x plus y equals 12 looks like because we just graphed it. You'll notice that the line of this equation cuts the plane into two parts or two sides. There's a part on the left side of the equation line and a part on the right side of the equation line. All of the xy points from the line will always add together to be 12. All the points to the left of the line will always add together to be less than 12, So all of those points will work in the inequality x plus y less than 12. I can pick any point on the left side of the line and plug it into the inequality to make sure. If I take the point x4, y3 and replace the x with 4 and y with 3 into the inequality and add them together, 4 plus 3 is 7, which is less than 12. I can plug in more points on the left side, and I'll guarantee that they will all be less than 12. So the graph of the inequality x plus y less than 12 is the whole half of the plane to the left of the line x plus y equals 12. That means that for the other side of the line, or to the right of the line, the graph of the inequality x plus y is greater than 12. That whole side of that half of the graph is a solution to that inequality. All I have to do is check one point from that side, like 9, 5, and plug it into the inequality. When I replace x with 9 and y with 5 and do the arithmetic, I can see that it's 14, and 14 is greater than 12. So we have three different situations here. If I pick any points from the line and add those values together, they will always add together to be exactly 12. If I pick any points to the left of the line and add the values together, they will always be strictly less than 12. If I pick any points to the right of the line and add the values together, they will always be strictly greater than 12. That was a quick overview of four basic types of equations and inequalities. There's a lot more to learning how to work with these than I've shown here. Let me show an inequality the way you might see it posed as a problem to solve. Let me read this inequality, then interpret it. It says that y always has to be less than 3 times whatever x is minus 1. So it says that when I pick an xy point and plug it into the inequality, how can I be sure that the point I pick will always keep the y value smaller than whatever the x value times 3 minus 1 is? I could randomly pick a couple of points and test them in the inequality, like the point 2, 7 or 4, 3, to see if they work. To test the point 2, 7, I plug in 7 for y and 2 for x and do the arithmetic on the right side to see if it's true or not. On the left side I have 7, and on the right side 3 times 2 is 6, and 6 minus 1 is 5. Reading the answer, is 7 less than 5? No, it's not. So that point will not keep the inequality true. How about the other point, 4, 3? Will that keep the inequality true? I have to plug in 3 for the y value and 4 for the x value. On the left side, I just have a single number 3, so I don't have to simplify anything on that side. On the right side, I have to simplify 3 times 4 to get 12, then subtract 1 to get 11. Now, is 3 less than 11? Yes, it is, so the point 4, 3 works in the inequality. I don't think anyone could tell simply by looking at the inequality which points will work and which won't. I know I can't, but if I graph this, then I can clearly see which points will work and which points won't work in the inequality. So here are the steps to take to find out which side of the xy plane will work for this inequality. First, we have to find the line that cuts this plane into two parts. To do that, we have to graph the equation y equals 3 times x minus 1 by momentarily changing the inequality to an equation simply by changing the less than sign to an equal sign. Now I have to find some points so that we can draw the line on this graph, so I'm going to make a chart and pick some x points. I can choose any x values I want, but it's a good idea to pick them close to 0 so the points wind up near the center of the graph and not way off too far so they wind up off the graph. I'll pick x as 0, 1, 2, and minus 2. Now I have to compute the y values that are connected to each of the x values I picked. I do that by plugging in the first x number into the x position in the equation, then doing the arithmetic to see what the y value is. If I make x 0, then 3 times 0 is 0, which just leaves minus 1 on the right side. So y equals minus 1 when I make x 0. Next, I plug in 1 for x and do the arithmetic to solve for y. 3 times 1 is 3, then 3 minus 1 leaves 2. So when x is 1, y equals 2. Next, plug in 2 for x, then do the arithmetic to see what y is. 3 times 2 is 6, and 6 minus 1 leaves 5. When x is 2, then y is 5. If you don't understand positive and negative number arithmetic, you can ignore the last one since 3 points are enough to plot the line. But I want to show one point with negative numbers. If I plug in minus 2 for x, then do the arithmetic, 3 times minus 2 is minus 6. Then minus 6 and minus 1 is minus 7. So when x is minus 2, then y is minus 7. Okay, so here are my 4 points I'm going to use to draw my line that cuts the plane into 2 parts. When x is 0 and y is minus 1, that means you don't move in the x direction, you just move down 1 in the y direction. When x is 1 and y is 2, that means you move 1 to the right and 2 up in the y direction. When x is 2 and y is 5, that means you move 2 in the positive x direction, then 5 up in the positive y direction. When x is minus 2 and y is minus 7, that means you move 2 in the negative x direction, then 7 in the negative y direction. As you can see, it looks like the points are all lined up, which they should be if we did our arithmetic correctly when finding the values. Now I can connect the points by drawing a line through all of them. If I pick any point from this line and plug in the x and y values into the equation, the y value will always be equal to whatever the x value times 3 minus 1 is. It looks like the point 38 is on the line, so let's check to see if it is. I plug in 8 for y and 3 for x. I just have to make sure that the left side stays equal to the right side for that specific point. The left side is 8, and if I do the arithmetic on the right side, 3 times 3 is 9, and 9 minus 1 is 8. So the point 38 is part of the line. Next, we have to figure out which side of the graph works for our inequality. It's either the left side or the right side of the line. I can pick any points from either side of the line to check to see if it keeps the inequality true. I'll pick a point on the left side of the line and another one on the right side of the line, and I'll test them both. The point x equals 1 and y equals 6 is on the left side of the line. I'll check that one to see if it keeps the inequality true. I have to plug in 6 for y and 1 for x. The left side is already simplified, so I have to do the arithmetic on the right side to simplify it. 3 times 1 is 3. Then 3 minus 1 is 2. Now I just read the inequality to see if it's true or not. Is 6 less than or smaller than 2? No, it's not, so that point doesn't work, which means none of the points on the left side of the line will work. It looks like all of the points on the right side of the line will always keep the inequality true, but we have to check a point from that side to be sure. The point 4, 6 is on the right side, so I'll check it. I plug in 4 for x and 6 for y. Again, the left side is already one number, so I have to do some arithmetic on the right side to simplify it. 3 times 4 is 12, and 12 minus 1 is 11. Now read the inequality to see if it's true or not. Is 6 less than or smaller than 11? Yes, it is. So that means that all the points on the right side of the line will work to keep the inequality y less than 3 times x minus 1 always true. So, what would the inequality look like for all the points on the other side of the line, or the left side of the line? If I flip over the inequality sign in our original inequality, that will work for all the points on the left side of the line. This was not part of the problem, but you should be aware of how all 3 of these different algebra statements are connected. Okay, so what did I have to do to find all of the solutions for the inequality? The y value has to always be less than the corresponding x value times 3 minus 1. First, I had to graph the line of the equation y equal to whatever 3 times x is minus 1. Then I had to pick points from either side of the line to see which one kept the inequality true. And finally, I could also write the inequality for the points that didn't work in our original problem simply by flipping the inequality symbol to the other direction. This was just an overview for you to gain an understanding about how these 3 simple concepts are related or connected to each other. This is only the beginning of an in-depth understanding of the language of advanced mathematics. Like learning any language, you first have to understand simple concepts in order to then understand more complicated ideas. If you haven't watched my video, Basic Algebra Part 1 and Part 2, I would suggest you do so. I also suggest you watch the video called Slope from Points and then Equations. That will show you more about graphing lines from points. Good luck and thank you for watching this video.